In the previous movie, we had just finished number 21A. So now we're going to look at the next question I ask you to take a look at, which I have to look back and see, a little technical glitch right there. It's number 31. So looking at 31, you've got this container. There's a container. Inside the container is water. Okay, you're going to put this little ball bearing into the water. The ball bearing is at a temperature of 525 degrees C. The water temperature when we began was at 28.5 degrees C. So 28.5 degrees C. So when I put this hot ball bearing into this cold water, it's actually not that cold, but when I put it into the water, what will happen to the temperature of the water? It's going to raise. So we're going to see how high the temperature will raise. Okay, I think it's going to go to a boil. It tells you that it's going to go, it tells you in the problem that there will be enough energy to bring it to a boil. So, let's find out how much energy is actually going to be required by the water to make it boil. So we'd have Q is equal to mCp delta T. We know the mass of the water from the problem is 75 milliliters, so that's 75 grams. Remember, the density of water is 1 gram per milliliter. We know the specific heat capacity of the water is 4.18 joules per gram degree C. And the change in temperature of the water from 28.5 up to 100 degrees would be 100 minus 28.5. So 100 minus 28.5, would that be 71.5? So if we multiply those three numbers together, we know how much energy will be required. So let me go ahead and get a calculator. I'll just work through this one with you. So 75 times 4.18 times 71.5 equals. So we have 22,415.25. So 22,415.25 joules. Okay, so that's how much energy it takes to get to the boiling point. You may remember first year class, I'm hoping that you do remember from first year class, that a phase change diagram looks like this. This would be melting or freezing, so melt in this case. This would be boil. This temperature is 0. This temperature is 100. So the water is beginning at 28.5. So we're right in here somewhere. Whoops. All right, so we're right in here somewhere. So we're going to go up and we're going to go over. The question is how many grams will boil away. All right, so we know that I think it gives us the heat of vaporization of water is 40.6 kilojoules per mole. Yes. And it tells us the specific heat of the metal ball. I went back to look at the problem for a minute. So specific heat is 0.5 joules per gram degree C of the metal ball. Now we know that the metal ball is starting at 525. So let's find out the change in heat for the metal ball. So we know the metal ball weighs, the ball bearing weighs or has a mass of 125 grams. We know that there are 0.5 joules per gram degree C for specific heat. And we know that the change in temperature of the steel ball is going to be from 525, we said earlier, down to 100, so that'd be 425 degrees. So the metal ball is going to lose this quantity of heat. So let's find out what that quantity is. It'd be 125. Oops, hit the wrong button on my calculator. 125 multiplied by 0.5 multiplied by 425. Final answer, 26,562.5. So once again, 26,562.5. All right, that's joules. So now we know that it took this much energy to raise the water up to boiling. But I didn't use all the energy that was lost by the steel ball. So the ball bearing lost this much heat, this much energy was required to make it water boil. So if I subtract those two numbers, so I'm going to take 26,562.5 and subtract 22,415.25. So I get 4,174.25. So the difference all right, now we know that while the water is boiling, there is no temperature change. So we're up here on this part of the graph. So the quantity of heat while something is boiling would equal to, it'd be related to that heat of vaporization. It takes 40 point, what was that number again? 40.6 kilojoules to vaporize 1 mole. All right, so we could, we know how many, we're looking to see how many moles of water would be able to be vaporized. We know that since there's no temperature change, usually we say that the quantity of heat while something is vaporizing is equal to mass times heat of vaporization. So there is no temperature change, you just multiply the heat of vaporization by the mass. The problem is, if we do this equation using this number, the units won't match. So we could, since we have this in kilojoules per mole, we could just say that there's 4,147.25 joules, which is equal to 4.147 kilojoules. So let's just go ahead and take that. So 4.147 kilojoules is the quantity of heat. We don't know the number of moles, so we just call that X, or question moles. If you want to just call it X, that'd be the easiest probably. And then we could say this is 40.6 kilojoules per mole. So when I divide that, I will get the number of moles. So 4.147 kilojoules divided by 40.6 kilojoules per mole is 0.102 moles. So that's how much water would vaporize, because it takes this many kilojoules to vaporize 1 mole. We had this many kilojoules. You could also do that by dimensional analysis. You could say 4.147 kilojoules times 1 mole over 40.6 kilojoules. Either way, you're dividing by 40.6. All right, so now you've got the 0.102 moles. You need to change that to grams, because the question said how many grams will actually be vaporized. And it is water, so we're looking at 18 grams per mole. So put moles down here, grams here. 18 grams of water is 1 mole. So 0.102 times 18, you'll vaporize about 1.84 grams. All right, there you go. Should be that should be the final answer for number 31. All right. So now we're going to go to number 32, but I'm going to have to open up a new page. So let's do that. We'll assume my movie got saved. Open up another blank page. Go back over here. Test it. Yep, still works. All right. Now the next question we're going to look at was 40. So I turn the page. Oh, don't have to turn the page. All right, so on 40, you've got the heated solution potassium acetate in water. Tells you that. You know you got 0.136 moles. So 1.36 moles potassium acetate. You have 15.3 kilojoules per mole. Okay, so if you multiply that by kilojoules over moles, you'd end up with kilojoules when you dissolve it. So 1.36 moles multiplied by 15.3. By the way, there's a negative sign on that. What's that mean? Energy is released. So you multiply that, and that'll give you a number of kilojoules of energy released. And I would change that to joules. Then you know that Q is equal to mCp delta T. You know you've got 525 milliliters, so that's 525 grams, because water's density is 1 gram per milliliter. You know the heat capacity is 4.18. You don't know the change in temperature, you're trying to find that, but you know that this number of joules goes in right there. And then the last thing you need to find is the temperatures. So you know you started at 25.1. You know since this is negative, the temperature is going to go up. So the T final will be more than the T initial, so it'll be T final minus 25.1. Then you just solve for your T final. So that one wasn't too bad a problem. Then the next question is 44. Okay, in 44 you got a bomb calorimeter. And a bomb calorimeter, for that bomb calorimeter, that's the completely contained calorimeter system. They don't give us a specific heat capacity, they just give us a heat capacity of the whole calorimeter. So you know that if you had 1.227 grams of sucrose, which is C12H22O11, you could change that into moles like this. Okay, I'll let you look up the weight. We know that the, let's see, what else? The base of the combustion, what should be the temperature change produced by the combustion? Oh, we had to look back and see what the heat of combustion is back in example 7.3. So it'll take me just a second to find that. There's 7.3, 7.3, 7.13. Example 7.3. Example 7.7. I'm going back in my book, just turning back to find out what the heat of combustion is in example 7.3. Okay, it's 5,600, it's 5.65 or 5,650 kilojoules per mole. So 5,650 kilojoules per mole. By the way, it's a negative because energy is released, of course, when you burn something. So that would give you the number of kilojoules. And you know that the specific, or the heat capacity, not the specific heat capacity, but the heat capacity of the calorimeter, for every 1 degree C, 3.87 kilojoules of energy are involved. So 3.87 kilojoules. And that would give you the delta T. That's it. So that one wasn't too bad either. The weird thing about this one is this concept here is not a specific heat capacity, it's just the heat capacity of the whole container and everything. So it's all lumped together. Remember we said you could have heat capacity of the whole container, you could have a molar heat capacity, or you could have a specific heat capacity. Molar heat capacity will be in kilojoules per mole or joules per mole degrees C, and specific heat capacity will be in joules per gram degrees C. That's specific. But that's not the case here. We're looking just the overall heat capacity, which does not quantify, just says the whole system raises 1 degree for every 3.87 kilojoules of energy in. So that was 44. Then 47. It's a negative P delta V problem, so just use that work is equal to negative P delta V for number 47. I'll write it down here, 47. Where delta V is a change in volume. And then once you have that pressure, since it's in millimeters of mercury here, you'll need to change millimeters of mercury to atmospheres for A, B, and C, which would be something that you need to do. All right, and atmosphere liters will be the first one you get when you just change millimeters of mercury to atmospheres. So measure pressure in atmospheres instead of millimeters of mercury. You have to make that conversion, then multiply by liters. All right, and then you need to make the conversion into joules and then into calories.
Okay.
All right, I'm going to stop right here because my wife is saying, hey, she has a question. So hang on.